Welcome to today's lecture. If you will, please turn off your cell phones. I'll turn mine off. Today's lecture is by Dr. Christy, who is the director of the Earth Systems Science Center at the University of Alabama at Huntsville. He received a PhD in atmospheric sciences from the University of Illinois and began working with Roy Spencer in 1989. And this team was awarded the NASA's Medal for Exceptional Scientific Achievement. In 2000, he was appointed by Governor Siegelman as Alabama's state climatologist. Christy was a lead author for the 2001 report by the Intergovernmental Panel on Climate Change and has been a contributing author to the other assessments. He published in various journals, including Science and Nature, and Journal of Climate. And Discover magazine recently had a feature story of Dr. Christy in their February 2001 issue, and NPR has aired a profile in 2004. And he's been called to testify on several U.S. Senate and House committees. And the Christies have two children. They're both very smart, Allison and Brian, and they attended Auburn University. Today is the 50th anniversary. Some of you may know about this. Sputnik was launched 50 years ago, and this event stimulated a lot of funding of research into space, and Dr. Christy began working with Roy Spencer when Spencer was a satellite meteorologist with the Marshall Space Flight Center. Dr. Spencer is now at the UAH as a scientist. Therefore, some of the information you'll be hearing today is kind of a spin-off from that launch 50 years ago, which stimulated research into space and satellites. Without further ado, join me in welcoming Dr. Christy.
Thank you, David. It's a pleasure to be here. It's been a long time since I've actually been down here to Auburn to speak to a group. I don't remember, Joe, when the last time was. It must have been 5 or 6 years ago. My son was a physics student at the time. My daughter since went here earlier. She was an applied mathematics graduate, and he's now getting a PhD up at Maryland in physics, studying neutrinos or something. I asked Joe, can he get a job if he knows something about neutrinos, because that's all I care about, of course. This is a pretty fancy thing here. Well, that worked. Let me see here. I'll tell you, high tech is interesting when it works. I want to give you a different sort of view on climate change than that which you've been exposed to, especially in the media. So this will be different. Just let me warn you about that ahead of time. So we'll just go launch right ahead into this. Michael Crichton is famous for the statement that consensus is not science. So whenever you hear these statements about 2,500 scientists, agree on something or other, right there you should know it's wrong. 2,500 scientists could never agree on anything. I just cannot imagine that. And as someone who worked on the IPCC, which is the United Nations thing on climate change, I know how that process goes. And I can assure you that there are many disagreements, that the final words do not represent the ironclad truth about something. It's an evolving document that often makes compromises, and consensus is really a political notion. It's not something that's based upon just things that are hard and fast. But Lord Kelvin told us what science was about 150 years ago. He said, all science is numbers. So we're going to look at a lot of numbers today. My favorite author said something about greenhouse effect, though. He said, some people will do anything to save the earth except take a science course. And it turns out science is hard primarily because it deals with numbers. And when we get all of our graduate students that apply, we can almost divide them into two groups, those that had lots of math and those that don't. And that's one of the best predictors there is in terms of how they will do in graduate school and the kind of science we have, how they deal with numbers. And being in Washington quite often, I deal with folks on the issue of global warming, for example, who don't have backgrounds in science or numbers, but they believe things about the way the world works or their view of the world, and those are very difficult folks to deal with. Well, let's start with some basic numbers about global warming. Carbon dioxide is a trace gas in the atmosphere. It has increased 35% in the past 150 years or so due to human progress. And the global surface temperature, as we'll talk about in a minute, rose about 0.7 of a degree in the past 100 years. Now, if you just have the physics of the problem and you say you increase carbon dioxide or double it in the atmosphere, the response of the Earth system at the surface will be about 1 degree C. Okay? That's it. No other processes, feedback or change in the, no other interactions occur. 1 degree C. That's where all of the uncertainties come from. What happens if you add more CO2? Does it change the cloud cover? Does it change the ice distribution? Does it change the color of the plants? You know, all of those feedbacks are where the enormous types of warming scenarios that are foisted upon you by the media come from. A climate model will have a trigger in it that if you add a little bit of heat due to CO2, then this trigger occurs and the heating goes off the chart. So that's where the uncertainties really are. Okay, you and I and the other 6.5 billion of us on the planet produce about somewhere between 7 and 8 gigatons of carbon dioxide per year, mainly because we burn carbon and it creates heat from which we get energy, to our great benefit, as you will see. About half of that stays in the atmosphere each year. So we produce 8 gigatons, about half of that is absorbed by the plants in the ocean and so on and removed. But the other half stays in the atmosphere, and with about 740 gigatons in the air right now, that means that the atmospheric rate is growing at about 0.5% per year. We're up to about 385 parts per million right now of carbon dioxide. Here are some of the basics. The climate is always changing. The global temperature is never static. It is either rising or falling. Sea level is either rising or falling. Glaciers are either retreating or advancing. And I assure you, or let me just ask the question, do you want to live in a world where glaciers are retreating or advancing? Think about that. Okay. This is a metric that you've seen quite a bit. This is the global surface temperature as produced by the Hadley Center in England. And what you see there are kind of 4 basic pieces of the past 150 years. There was a cooling down to about 1910. Yeah, a cooling down to about 1910 or so. And that's been attributed to Mother Nature. There was a rapid warming up to about 1940, and that's been attributed to Mother Nature. There is a slight decline from about 1940, 45 to about 1975. That's basically been attributed to Mother Nature. This rise to the present day has been attributed to humans. And that is a big question. You know, are we responsible for what you see on this picture of a rising surface temperature in the last 30 years or so? I ask a question there. Is this a proper metric to measure what humans are doing on the planet? And the answer, I will show you, is no. So is the mean surface temperature an appropriate index for the greenhouse effect? Well, the mean surface temperature is an average of 2 things. It's the average of the daytime high and the average of the nighttime low. So daytime plus nighttime divided by 2. When you show something to Congress, you know, you have to really make it simple. Daytime, nighttime divided by 2. Then the chairman of the committee asked Dr. Christy, what do you mean by correlation? And you think, golly, well, where do I start, you know? Anyway, so let's look at the day versus night temperature. By the way, I understand some people are around the country watching this right now, so wherever you are, I hope you are able to see what's going on here. If you look at the nighttime temperature on the left, you see that what happens is the surface, the air near the surface decouples from the air aloft over land quite often. So that very cold, heavy air settles right here and is disconnected from what happens above. Now the daytime, because the surface is heated, there's lots of mixing. So if you want to know what's happening in the upper air, where the greenhouse effect is largest, where the signal is greatest, you would want to measure what's happening in the daytime, not the nighttime. Here's another reason about that. In the nighttime, like I said, in an undisturbed place, you have warm air that really doesn't change much from day to night. When you go up 1,000 feet or more, the temperature doesn't change much from day to night, whereas the temperature, of the surface does. But if you add buildings, if you add aerosols or pollution, many, many things actually disrupt this delicate inversion that sets up, and you create a situation in which this warm air is mixed down so that the nighttime temperatures show a rapid warming, not because of anything to do with a greenhouse effect, but because of the way development has occurred on the surface of the earth. Okay, let's look at Alabama. This is a paper I published in 2002 and is updated to 2007 to include our very hot and dry summer. And we see here the daytime temperatures here, and this is true for all of Alabama, not just northern Alabama. This is just a very specific kind of study. But the temperatures here have been falling. In Alabama, the temperatures of our state have been falling for the last 115 years. There used to be a citrus industry down in Baldwin County. Now you have to go to Orlando or southward to find the citrus industry. And many other things are available to demonstrate that it's not as hot as it was, especially back in the 20s, 30s, and the 50s, early 50s. In fact, here's something else. Rainfall in Alabama has risen in the past 115 years. Now, we've had a couple of dry years here recently. You see right there on the end, 2006 and 2007. And as a state climatologist, I have to be on conference calls all the time to define the drought indices for our state from which federal disaster declarations are made and so on like that. We're having a dry spell right now for sure, but that's a departure from the long-term trend. And I think I saw something even came out of Auburn that said, we expect to get drier and hotter when the evidence shows we are getting cooler and wetter. So, don't extract yourself from the real data whenever you start thinking about climate change. Okay, so we're getting wetter and cooler here. But let's go to a place near where I was born and raised in California. This is Darwin Glacier in Fresno County, California, up in the Sierras. That's about 4,000 meters elevation. You can see that this situation in 1908, the glacier was, looked a lot bigger than it does right now in 2003. That glacier is going away, basically. And pictures like this are often shown in climate change stories to try to excite you about the disaster coming, and fail to tell you, for example, that glaciers like this are about 800 years old, that they didn't even exist a few hundred years before that. Most of the glaciers in the western U.S. are less than 5,000 years old. So there are periods, certainly the last 5,000 years, that were much warmer than it is today. But it turns out glaciers are terrible thermometers. Let's go to I hope you can recognize California there. Here's the coast. Where's there's Monterey Bay right there. Here's the San Francisco Bay Area. The Sierra Nevada mountains are right here, and this picture was taken because of the fire down there in the Southern Sierras. This is the Central Valley of California, and there's something very unusual about that in this photograph. This is in July. You see all of that green? That shouldn't be there. It should be light tan, like you see on the edge here in the lowest elevation of the foothills. That's a desert. Gets less than 10 inches of rain a year. It's a desert. Yet it's all green because of irrigation. And I grew up, playing in irrigation canals and running through forests, and we'd always ride our bikes, on the east side of the orchards in the afternoon because the wind would blow from the west and blow through the orchards, cool, from the irrigation, and it'd be cooler because it's always 105 or something like that normally. So irrigation has really changed the landscape there and the development of the surface. That should have an impact. Now, if you go to climate change models, all of them show this feature right here, where it says, for if greenhouse gas warming is occurring in California, the mountains should warm much faster than the lowland areas. The mountains should warm much faster than the lowland areas. Well, let's go to the data. This is a paper published just last year. It was very complicated work on trying to create the most robust, statistically verifiable kind of time series of temperatures in the valley and the nearby Sierra foothills. The orange is what we got for the Valley, California. Rapid rise. This is on the order of 5 degrees C per 100 years. This is a tremendous warming. In the very adjacent foothills, the temperature has a slight decline. That tells you right there, this is not a greenhouse gas effect. It's going in the opposite way of what greenhouse theory indicates. What it does indicate, I think, is what I showed you in the 2 slides before, is that changing the surface character changes the way that nighttime temperature cools. And because of the urbanization and the irrigation that has just changed that whole valley to a dark, moist, vegetated plain, that the nighttime temperatures just can't cool off like they used to. And so that is, in a sense, is a false signal. It's not greenhouse warming that's occurring there. It's development of surface warming that's occurring there. It's humans. There's no question about that. Humans are causing that rise, but it's not greenhouse effect. I deal a lot with California, being a native of that area, and their governor, or their governor is has a very strong feeling that this greenhouse thing is something that needs to be attacked and dealt with, and so on. And the science here that is published says, if you want to change the temperature, depopulate the valley and return it to a desert. You will change the temperature back to what it was if you do that. But dealing with greenhouse gases will have no consequence at all. Yet, what orders are being signed, executive orders in California, now in Florida, are to deal with somehow greenhouse gas production. So the main point is that average surface temperatures at this point, the daytime, nighttime, is a poor proxy for greenhouse detection because of nighttime contamination of human development. And it actually overstates the warming. Now, this is Georgia, just to show you that same thing is happening in Georgia. The temperatures have been slightly declining in that state as well, both summer and winter. What do models suggest for the southeastern United States? The observations, as I showed you, have a declining temperature. So several models were taken and tried to reproduce the last 100 years or so of southeastern climate. Every single one, and there's more than this that I could have shown. Every single, every single one says the temperature of the southeast should have risen in the past 100. It should have risen. And as one of the modelers said, my model is right. It's the world that's wrong. Let's go to upper air temperatures, because I told you that daytime temperature, because of the mixing with the air above, is a better proxy for what's happening in the upper air. And this is the reason. These are 4 panels from 4 different models. And if you look at just one panel, this is the South Pole, this is the North Pole on the horizontal, this is the vertical axis. So the stratosphere is up here, the lower atmosphere we call the troposphere is down here, and these are greenhouse gas simulations. They say, this is the difference between a control run and a greenhouse run in a climate model. These are 4 different models, and they all show basically the same thing, that the biggest signal you can find is in the tropics and in the troposphere. That is where the signal, in other words, the change in temperature versus the background noise, is by far the strongest. So if you want to look for a place where the greenhouse effect is supposed to be occurring and most clearly delineated, you go to the tropics and to the upper atmosphere there. Well, we do that. I have a number of papers, just published one this past February, in fact, that shows here is what theory says, and these are all the observational data sets of how fast the temperature is changing in the upper air. And they are all, except this one, much below. And this blue one here is the University of Alabama in Huntsville, our group's production, and you can see from these other independent data sets, we really nail the median of those and have by far the most consistency with independent data. This other satellite data set right here It turns out when we examined it very carefully, it had a huge error characteristic to it, and so it has a very large error bar to it as well. And so easily the observations indicate that what is happening with the temperature is not what you see in climate models. This is our satellite data set, and I've updated it through September 2007. And you can see that since the El Nino of 1997-98, it's kind of just been bouncing around a little bit. There is an upward trend in it. I suspect is due in part to the extra greenhouse gases, but the magnitude of that trend is much less than what models suggest. So the main point here is that better proxies, daytime surface temperature and tropospheric temperature, show only modest changes and no change in the southeast, neither of which are produced well in models. So what about the greenhouse effect? Here is something that I hope you will take away with you. There are about 4 or 5 things that kind of punchlines I hope you take away. This is one of them. Water vapor and clouds dominate the greenhouse effect. Water vapor and clouds by far dominate the greenhouse effect. And they are variable. I mean, they vary. The greenhouse effect of clouds and water vapor varies more than the whole CO2 effect. Okay? Climate models suggest this. Well, they don't suggest it, they show it. That when you add CO2, that the cloud and water vapor effect multiplies the CO2. In other words, it's a positive feedback. Add a little CO2, clouds and water vapor greenhouse effect gets real big, and so the whole thing adds up to a higher and higher temperature. So just for a picture, this shows the clouds and water vapor activity in terms of the greenhouse effect, and then the others, the carbon dioxide is this one right here, and the other gas is right there. So the question is this. We know carbon dioxide is increasing. We know that its radiative force will increase. I mean, there's no question about that. We measure CO2. There's more of it in the air. It's a radiatively active gas. It will increase that forcing. But for the climate system, what's going to happen to this one right here? Is it, as models indicate, going to make that go even more? Or could there be negative feedback? Well, 2 months ago, Roy Spencer was the lead author on a paper that we published in which we got the satellite data to show every type of cloud and precipitation system that goes on in the tropics and how they vary with temperature. And it turns out there is a negative feedback. In other words, as temperature rises, the way the clouds respond is to cool the climate. It's like a thermostat. It turns out that the clouds that cause warming, cirrus clouds, shrink whenever the temperature goes up, and that allows radiation to escape its face. And so it cools. It's an automatic kind of cooling mechanism. This is in the opposite direction in climate models, and that missing a feedback like that will lead you astray very quickly. There's still more research to be done on this, and Roy is working on some further papers that he's also submitted to show how difficult it is in climate models to present the way the real world operates. And when you think about it, the climate system of the real world has millions of degrees of freedom. Do we understand every single one of those so well and represent the equation so accurately that we can forecast into the future? And my point of view, the answer is no, and partly because of the data sets we build and compare with climate model output. And by the way, there are very few people in the world who actually build the data sets from scratch like we do up in Huntsville. Okay, so the main point there is that most greenhouse gas components, the most important, clouds and water vapor, are poorly understood and poorly characterized. In fact, there's a paper that just came out last week, Sun et al., in which he did a different study but showed that models overestimate that feedback. And that's why they show this warming about which everyone gets so excited. Well, let's look at some data. And I love this part. Cold places. What about cold places? You've been inundated with information about the Arctic sea ice, that the Arctic sea ice has declined in the past 30 years or so. And especially in this past year, it's been the lowest that's ever been measured from satellite, as you can see from this daily chart of the anomalies of the Arctic. This is the northern hemisphere, up there at the North Pole ice. Here is a temperature record of the Arctic. Well, it turns out it's actually been hotter just in the past century than it is today in the Arctic, back in the late 30s. But we only have a satellite record, as you can see there, from that thing. So we're not sure, when this rapid warming in the Arctic occurred, what happened with the sea ice at that time? Did it then expand as the temperature fell during this period? And we are watching it during this period of rising temperatures. So having a consistent data set for a long time period is the gold standard of climate work, and we just don't have that for this Arctic sea ice. We do know, however, that the North Pole regions were 4 and 5 degrees C warmer about 5,000 to 6,000 years ago. The forest went all the way to the edge, to the Arctic Sea. Greenland is important. I'll tell you why in a minute. But here's the time series of Greenland, the summer temperatures. Because if Greenland's going to melt, it's going to melt in the summer. It shows decades of warmer temperatures there in the past 1940s, 1960s, and so on. Let's go back further. If you go back 2,000 years, this is the temperature record of Greenland. 1,000 years ago, it was much warmer for a century scale period than it is now, and Greenland did not melt. Now remember, to get the kind of sea level rise that an Inconvenient Truth shows, or a couple of extreme scientists talk about, you've got to melt Greenland, all of it. You've got to melt all of it. Greenland was much warmer for century scale periods 1,000 years ago. It didn't melt. Let's go back 10,000 years. You go back to the period about 6,000 BC to 2,000 BC, it was much warmer even then, much, much warmer for 4,000 years, and Greenland did not melt. This is the kind of evidence I presented at a trial last May in Vermont. I was asked to give information to federal court. It was a federal court case in which Vermont had adopted the California AB 1493 regulations. These regulations basically said the average fleet of cars sold in California, and now these northeastern states, has to be 43 miles per gallon. Okay, the average. Now, you might be able to make a few cars, that get up that high, but the average of your fleet has to be this. Well, the automobile manufacturer said, this included Toyota, Honda, and the whole group, said, you can't do that. You can't just mandate that by 2016. So, there's this 8-year thing in which this whole new kind of technology has to be arrived at. Now, the court case, as I'll talk about here in a second, in May, dealt more with the legal issues of, can the states require a mileage standard, or is that the federal government's situation? And is it technically possible to do? The environmental side said, oh yes, for only $1,500 a car, you can have the average be 43 miles per gallon. The automobile manufacturer says, no, it's $5,000 a car, and here's the evidence to show that, and so on. So that was the big question there, but the judge said, well, I want to hear about the motivation of the law. Why is this law here for the global warming situation? So there were 2 days of testimony about the climate, and the environmental side brought forward 2 witnesses, and then I was asked to go up to speak, to provide evidence from my research and things like this to counter the other side. I was not paid. In fact, I took vacation. I paid my own because I don't receive money from corporations or industry or anything like that, to make sure that everything's above board on this. And so I showed one of the fellows from the other side said Greenland's going to melt in the next 100 years. In the next 100 years, Greenland's going to melt. And I said, it's been much, much warmer in the past for thousands of years, Your Honor. It was a bench trial, Your Honor, and it did not melt. All I had was evidence. Let's go to Alaska. The temperature goes up and down in Alaska quite rapidly, and this is a situation in which polar bears tend to come in. And I have a story about a polar bear story about me and the anchor of CNN on a live exchange, but we'll skip that. Anyway, it turns out polar bears do real well, no matter if it's warm or cold. Their numbers have risen by a factor of 3 in the past 40 years, because not because of climate. It's because of the Wildlife Act and the quota system that was established, because once the Eskimos, the Inuits, had the ability to use high-powered rifles, polar bear populations just plummeted. And it might have gone extinct. But with the Wildlife Act, I think it was 1972, and the quota system established, then the polar bears recovered. And so there's quite many, many more now than there were 40 years ago. But they're pretty hard to count. But we do know that places where they are being counted, that the populations are healthy. Let's go further south from Alaska to Kilimanjaro. I was a missionary in Africa for a while, and I saw Kilimanjaro a number of times. I taught physics and chemistry to high school students in Nyeri, Kenya. The temperature in East Africa is not rising at all. But if you look at that graph right here, this is the snow coverage of Kilimanjaro. It is definitely going down. There's no question about that. It's 10% of what it was back in 1880 when the first surveys were taken. But when Ernest Hemingway wrote Snows of Kilimanjaro, it was already half gone. And it's hard to blame any of this on human effects. Turns out it's the natural variability of that system. That ice has melted completely away before in the past 12,000 years and come back a number of times. So, in fact, this past year, 2006, they had a huge dump of snow. It buried one of the meteorological instruments up there. So who knows, but this might be a change back to a more normal condition because it's always below freezing up there. The situation here is likely one where there's less cloudiness and snowfall now, and that's from a natural variability standpoint, and that's why it's declining so rapidly. Let's skip this one. Now let's go to another favorite place of mine. We've gone south, we continue to go south. This is the Antarctic sea ice. There's actually an upward trend in the sea ice extent of Antarctica. This is a story you will not hear about in the newspaper or on a show that wants to scare you about global warming. The sea ice around Antarctica is not only rising, but 2 weeks ago, it reached its all-time record maximum extent. It has never been, in at least the satellite record, this large before. Now, why was there not a story on the front page of the New York Times telling you that the Antarctic sea ice reached its all-time maximum extent when just a few months ago there was a story about the Arctic reaching its all-time low extent? No climate model can reproduce this at all. Why is it getting colder in Antarctica and the sea ice increasing? Snowfall, if you see warm colors there, that's where snowfall is increasing and the depth increasing. And so most of Antarctica is accumulating snow, which means it contributes to sea level drop. This is just temperature of Antarctica. The point here is in the last 4 decades, the temperature has fallen in the Antarctic continent. What about sea level rise? It's always rising or falling, and it has a slow rise right now of about 1 inch per decade. And if you see, this is the future projections, this one right here, that's Antarctica. Antarctica is projected to suck up water from the ocean and dump it on the continent and therefore contribute to sea level fall, while Greenland is supposed to melt a little bit and contribute to sea level rise. What about extreme weather? Here's a tornado history. Have you heard many times that tornadoes are going to get worse because of global warming? And the evidence says the opposite. If we're warming, tornado frequency is going down. Hurricanes, they go up and down, but there's no direction really either way. There are cycles in hurricane projection, in measurements of hurricanes, but there's no trend really in frequency or really intensity either way. But let me tell you this. Will the damage from hurricanes increase? Absolutely. We just put more stuff in the way of hurricanes down on the coast, and we're just saying, come on, hit me. And as a state climatologist, I deal all the time with people who have to have design criteria and so on for building something on the coast, and I just say, don't do it. A hurricane will come. Here's Frederick, here's Ivan, here's Opal, here's Katrina, It's going to happen. And I was pleased to see that Tyson Krupp put their plant, dealing with them further north of Mobile, to try to avoid a lot of the problems there. Look, hurricanes happen, okay? And we're going to see some big tragedies in the future or when Miami gets hit by a Category 4 or 5, or one of the other, Wilmington or something like that. Katrina was a Category 3 when it hit New Orleans. That's typical. So we've got some accidents waiting to happen out there. There's about 95 hurricanes per year in the world, and that number has stayed steady. Some basins show rising, some basins are falling. This is drought, and if you see blue on that chart, that means droughts are getting fewer and less frequent. I see a lot of blue on that chart. I hear the phrase all the time of people scaring about greater droughts, worse droughts, and so on like that. The evidence, the observations do not go along with that. So I don't think global temperatures are rising to an extent that's really that remarkable. Sea level's going up about 1 inch per decade. Better be ready for that. And severe weather's not becoming more frequent at all. And when I'm, especially before Congress and speaking for the energy committees, I just resist this notion of demonizing energy because, especially after my time in Africa, the simple fact is without energy, life is brutal and short. And I can assure you that's the case. In 1900, we had 56 billion human life years, the energy technology of the day, 1.6 billion people times 35-year life expectancy. Today, it's 8 times greater. Now, to me, that's a spectacular achievement, and I say that because as a grandfather, I happen to know that a grandson who wears his little Auburn thing every Saturday, in the fall, that when he comes up and grabs my knees and, smiles like that, I'm experiencing something in life that 100 years ago was very unlikely to experience because of what has happened with the energy technology of the day. We live longer and we live better. That is the benefit that demonizing energy never takes into account. And I find it incredibly presumptuous of people to just claim we need to use less energy, we need to get rid of this energy use and go back to living, a very primitive lifestyle. As I said, I lived in Africa for a while and taught physics and chemistry, and I taught people that were just delightful. They really worked hard. I'm really impressed with the folks that were there. But here's the energy system in Kenya. In the upper right is the energy source, forest. That's the source of energy. Here's the energy transmission system, the backs of women. UN estimates that each one of those loads that they carry per day is 40 pounds, and the length is 5 kilometers per day. And then that wood is burned. This is the tragic part. It's burned inside the hut, and the kids breathe that smoke and contributes, the UN estimates, between 1.8 and 5 million deaths per year. I mean, that's how many kids are dying now because of respiratory illnesses caused by this energy system. So what do you want to do about, suppose you do want to do something about global warming, and I understand that probably many of you here think that global warming is a serious problem, so something must be done about it. And here are your constraints. You still have to supply affordable energy. Energy use the demand is growing like crazy, so that still has to be one of the constraints. And if your other constraint is reduce CO2 emissions substantially. Well, as I said, California did this. They passed a law to reduce emissions. It turns out 26%, which is like 43 miles per gallon. And as I said, the trial was in federal court in Burlington, Vermont, April and May of this year. So I was asked to answer these questions. What would the impact on global surfaces be of adopting and adhering to AB 1493? Now, California is famous for passing laws that they never follow. I mean, Europeans are very good at this. They pass laws, pound them their chest and say how good we are, and then they never, adhere to what they go. But I'm assuming the law is passed and adhered to. And I did some very conservative things. I made sure I was overestimating the impact of this law, so no one could challenge the numbers. So this is the best estimate of temperatures from the IPCC for the next 100 years. I don't trust it, but let's just assume that is the best estimate of what the temperatures are going to be for the next 100 years. I applied AB 1493 to the entire country, okay? And I'm going to overlay the result on this picture, so watch carefully. That's the result of AB 1493. In other words, there is no result. In fact, if the entire world adopted AB 1493, the difference would be 0.03 of a degree, an amount we cannot measure, we cannot detect. So, I'm thinking like a scientist, you know, dumb me. I'm in a courtroom. You know, I'm thinking like a scientist. The evidence shows this law has no effect. So what am I going to conclude? Well, the law should be thrown out, right? I mean, that's just what I would do. And so the answers were just what I've showed you, that there's essentially no detectable effects. Well, Judge William Sessions ruled just about 3 weeks ago that AB 1493 is legal and can be enforced. And I'm thinking, what is going on? And in the decision, on page 46, he has this in there. Plaintiff's expert, Dr. Christy, estimated that implementing the regulations across the entire United States would reduce global temperature by about 1/100th of a degree by 2100. Hansen, which was the who testified on behalf of the defense, did not contradict the testimony. I mean, the numbers I did were just solid. And so, though he recognizes the science and the evidence, he went on with a decision that just contradicted what the evidence showed. But this is when it gets into a court system, a system like that, you really can't control it. And this is a funny cartoon that came out in the Detroit Free Press. The court mandates 43 mile per gallon cars, 1,500 square foot homes, size 32 pants, and I'm out of there, size 4 dresses, and so on. It's interesting when courts start mandating engineering and physical law. We hope that that wouldn't happen, but there you have it. But ask the question, what could make a dent? Can you make a dent in those CO2 emissions? Because, remember, energy demand is growing. It will grow because it means so much to life, to human life. Without it, life is brutal, okay? Well, let's build 1,000 nuclear power plants, 1.4 gigawatts each, put them online by 2020. Okay, the one that Browns Ferry just started up here, that's a 1.2 gigawatt plant, nuclear. Okay, here's the best estimate. Now, what would 1,000 nuclear power plants do? About 1/1500th of a degree by 2100. This is at the level we can almost measure. It's right at the level we can measure now. And so to get the first and the smallest detectable thing, you need to be for 1,000 nuclear power plants right now. Start building them now. Have them ready by 14 years from now. So the main points: without energy, life is brutal and short, and do something about global warming initiatives. When you get down to the science and say, this is what's going to happen if you adopt this initiative, you see nothing can happen, really are not going to affect whatever the climate's going to do. And so a rational approach, I think, is to adapt to what you observe. Observe the climate, what it's doing, adapt to that. And that's where you spend your money, because then you know you're getting your money's worth, because you're spending on what's actually happening. And I think in 50 years, we're going to be surprised not by climate change, but by the inventive minds of our scientists and engineers, unfettered by mandates, as they discover profitable. Remember, if you discover new ways to get energy, you're going to get rich, okay? So greed really does motivate a lot of things. And we're going to find ways to generate energy without carbon emissions. I am astounded at my son, who's a graduate student in physics, at what's available to him to do his research today versus what, you know, many of us had when we were in graduate school. The punch cards, you know, at best, and the paper tapes and so on. Boy, we had a 110 baud printer. We thought that was the greatest thing in the world. So we're going to see some fantastic things coming. So in the 20th century, transportation was dehorsified. I think in the 21st century, energy will be decarbonized. This is my last slide. 2 cavemen are sitting there. Something's just not right. Our air is clean. Our water is pure. We all get plenty of exercise. Everything we eat is organic and free range. And yet nobody lives past 30. That's the difference between having energy and not having energy. And so with that, I'll close. So thank you very much. You have some...
We have a microphone here for anyone with questions. If you will, come by and state your name and then the question.
Hi there, my name is Matt Williams, and Dr. Christy, you are a very charismatic and well-spoken speaker, and I can see why you're the darling of the fossil fuel industry and by free trade extremist groups. There are thousands of authors on the IPCC
I'll say
along
thank
with you.
you.
You are the darling of these groups. There are thousands of authors on the IPCC with you. That group has analyzed 29,000 data sets. Can you convince this audience why a very small minority of scientists are the ones that we should follow for policy?
Well, Matt, the question about science is not done by voting. It's done by science, by the numbers. Did you have any question with any number I showed? Okay, were you convinced that climate change is catastrophic? Were you convinced that we can do something about whatever the climate's going to do? Okay, well, let's back up then. First of all, there are not thousands of scientists that participated in the IPCC, like you say. The Working Group 1 had there were about 700 or 800. The vast majority are not climate scientists. They are picked by their countries to represent their country's political views and things like that. So very few that were actually climate scientists. And remember the IPCC, and this is where science kind of gets skewed. The authors of the IPCC are also the reviewers. So it's not what you think in terms of peer review. Whoever gets selected to be there are the ones that control the outcome. Most of the material in the main text of the IPCC, the big thing that I had parts in, is pretty good. You know, it has this or this. You know, be cautious about this, we're not certain about this. But when you get down to the final summary for policymakers, the pressure is to come up with punchlines. And there's about 30 people that work on that. And so don't translate this 29,000 data sets into what 30 people are saying in punchlines. And I think if you look at a lot of those 30,000 or whatever data sets there are, and I don't believe 29,000 by the way, you'll find a lot like I just showed that show that this catastrophic message is not there in the real data. And I think now it's coming to me. Some of those data sets are not data sets. They're model projections. But because they're numbers, they have this feel about being data. But they're only projections. So, and, you know, like I said, I don't take any money from the fossil fuel industry. But I'm probably alive today because of the fossil fuel industry. And you probably are too as well. And I hope you recognize that. I really do.
Mark Barnett in civil engineering, and let me say I appreciate you coming down here and giving this talk. I enjoyed it. Glad I came. I have two questions, I guess. The first, do you receive any money earmarked from Congress?
The university does.
Do you receive any money directly earmarked from Congress?
In some of those grants, the research I do, here, maybe this is the answer to your question. If money is earmarked for the university, you propose to the agency to receive the money, and you are then required to do the research that you propose that's accepted by the agency. And so that's the way it works, just like a grant.
So, well, are you getting money without the normal peer review process? I know the difference.
So do I. I think you
well,
don't have...
so that's... Not me.
Are you paid by the state of Alabama? I mean, are you paid by the state of Alabama?
Yes, but
there you go.
But I did not get research money without the peer review process. Okay,
Look, just to clear that up, we do fundamental research for agencies from which the money comes.
Sure.
And this research is tornado, hurricane, irrigation, air pollution. We establish climate data stations here. In fact, Alabama is the model for these climate station networks right now because of funds that come through what we call, or what they call, the directed funding process. Okay. By the way, the legislator is accountable. And so this is a way in which, because he's elected, or she is elected, that the constituency is dealt with.
For the record, I do federal research. I don't do research on anything earmarked specifically from Congress. It's not peer-reviewed. The other question is, I've seen you testify before Congress, and although I would characterize your testimony and the testimony of the different sides a little bit differently than you did, but my question is, although I guess it is helpful to have people like Michael Crichton and P.J. O'Rourke agree with you, does it give you a pause? Does it give you pause that when the National Academy of Sciences, the U.S. National Academy of Sciences, which was formed specifically to advise the U.S. government on science-related matters, when they look at the same numbers you do, plus a lot more that you didn't show, that they come up with a different conclusion than you do?
Well, it doesn't bother me. I actually build the data sets that go into that. And I believe, the National Academy, I said on one of the panels of this, doesn't quite come across with the dogmatic results I think you're implying about climate change. We're talking about people. There are people. Well, that's people, okay? And let me, here's a news flash. Scientists are people, and people believe what they want to believe. And I would say many of those that were on that one panel you're probably talking about, climate change is something in the 21st century, probably disagree with a lot of things I said, but they can't disagree with the numbers. And I'm probably the only one that would have been on that panel that actually builds the data sets from scratch. And I can't remember all the people that were on it, but that's why, I can stand up here, I think, on pretty firm ground, because we go right to the heart of the data, the digital counts from the satellites, the actual paper records from Kenya in 1902 and so on, and build these data sets from scratch, and we don't see the catastrophe that is very popular to popularize today.
I'm David Bransby, agronomist here, and like to think that I'm very scientific in my approach as well. And I have two questions about your data. Firstly, you talked about temperatures going back 10,000 years. How did they estimate those, and how confident are you in those estimates? And the other thing is, there were a couple of times where you used straight lines where just an eye view of your data looked like curves would have been better. And in other words, you used a straight line, but it looked like a curve would have been better. Would you like to comment on those?
Okay. The first question, and this one always is asked: how do you take the temperature 10,000 years ago in Greenland? This is done by borehole. When a hole is bored for the ice core, it's lifted out, and so people look at the striations of that to determine various things, but the hole is left. So they put a casing in and fill it with an alcohol that doesn't freeze. And after a few years, the temperature down through that column equilibrates. It turns out the only forcing of temperature for that column is from the surface. And so if there is a very warm period, that will propagate down through the borehole. And on these, for example, you're really measuring the temperature from 8,000, 10,000 years ago when you go further down. The deconvolution of that's pretty complicated. You have to, the diffusion equation operates very strongly as you further down you go. That's why the temperatures get smoother as you go back in time. But these are the kinds of things that are reproducible. You go to another place, drill the borehole, and you get the same kind of result. The Ural Mountains, for example, also show the same results of the much warmer temperatures back in the period before. So it's a thermometer that's dropped down in this liquid that's very deep, and the temperatures are recorded, and the deviations from a reference curve tell you if it's warmer or colder. What the second question was?
Straight lines instead of curves.
Straight line. Oh, yeah. What's the model you want to fit some of those things there? It is most popular today to talk about trends because that kind of represents the slow accumulation or non-accumulation of joules of energy in the system. But probably the same kind of question is that a significantly different value from zero? And some of those probably wouldn't have been significantly different from zero. But yeah, you could fit a polynomial or anything like that.
David LeBand from the School of Forestry and Wildlife Sciences here at Auburn. Pleasure to have you here and really appreciate you being here. I feel kind of bad that certain people would like to attack you personally rather than on the merits of the science, and so I'm not one of them. But I would like to address two, I think, straightforward questions for you. One, I'll ask them.
Two-parters because I always forget the second one.
No, you'll remember these, I think.
Okay.
The first one is, if 5 billion people on a planet do a stupid thing, is it still a stupid thing or is it a smart thing? And the second one is, we've had a lot of time to start looking at a lot of numbers over the last 30 years. Could you care to speculate about why it is that global warming seems to have gained a lot of traction just very recently?
Okay. If you, on the first question, the 5 billion people or 6 billion, whatever it is, do something stupid, well, that's a moral call, you know. Is it stupid to want to live longer? And if you boil that question down to that, you're going to say, then it's not stupid to create energy for you to live longer. But, you know, people do, well, you know, like I said, stupid is a moral judgment, and so it's pretty relative. Second question is, why in the last 30 years? Because many of you, I can tell, can remember 35 years ago when the Ice Age was promoted as that's the next terrible thing that's going to happen. I remember it very well because I was studying climate at the time. We were warned by some of the same people that are warning you about global warming that the Ice Age is going to be the killer for us all. Boy, there are a lot of reasons, and the motivation varies from the media attention to if it bleeds, it leads. You know, if it's dramatic and catastrophic, we put it on the front page. You know, how I did keep one paper, I wish I had it. It was from USA Today that had our satellite temperature on it. It says, world temperature is normal. Little bitty thing in the back page. But that doesn't happen. It's the worst, you know, and this sense, maybe this gets to your question. There is a sense in which we want to blame ourselves or find the cause of things we see in a nonlinear, dynamical, chaotic system. Unfortunately, these kinds of systems have solutions that vary, have multiple solutions for the same forcing. And to think we can pin whatever little change occurs on a very primitive notion of how the system works on us or something else, an asteroid or something, is a little bit of hubris, I think. We, you know, we are mere mortals, and this system is very complex. And I think taking that approach would be better, but funding is wrapped up in it. As anyone knows, if your stuff is on the front page, you can get more funding, and you can promote your notion that you're going to save somebody's life or, you know, business or someone. That helps out. And some people like a lot of attention. Some people are just very committed and believe, I mean, truly believe that this is a disaster that needs to be avoided. So there's all kinds of motivations, I suppose.
Hey, I'm Zach Burrell. I'm a physics student here, and I'm actually currently taking an environmental physics class. And the other day I gave a presentation on the ocean currents, and while preparing it, I came to understand the importance that they play in the global climate. And I was just wondering if you had investigated some of the effects of higher CO2 levels, or the CO2 being introduced to the atmosphere by humans, what effect that has had on deep ocean currents like the thermohaline circulation.
That's a good question. By the way, there was one other point to the last question, too, that I forgot to address. I don't mind people challenging me on anything. So I hope sometimes I might preach in my response. You know, I used to be a minister in Africa, but that's okay. I don't mind at all being challenged. I mean, I've been up on a federal court case with $1 million a year paid, or probably someone paid that much to try to attack me in a number of ways. So I've been there and done that. So I appreciate any challenge that comes. The question about the thermohaline circulation or whatnot, if you've ever seen the movie Day After Tomorrow, that was a movie in which the ocean circulation was supposed to shut down. Well, some of you, I think, just on the back of the envelope think, boy, there's a lot of inertia in the ocean, and shutting down the ocean is just something beyond our control. Yeah, the most recent research shows that this is such a huge circulation and supported by such strong physical constraints that it will not shut down. What has happened in the past, prehistoric past though, has been sudden surges of fresh water that go out over the North Atlantic. And fresh water is lighter than seawater, and so fresh water can be cooler than the water below it, and that prevents the heat exchange to the northern hemisphere, that then if you prevent that heat exchange to the polar regions, they freeze over. And so we think some of the sudden cold events that the prehistoric record shows probably happened because of surges of fresh water that went out into polar ocean. But in terms of the ocean circulation shutting down, that's not in the cards. The data show that that's not happening.
First, thank you, Dr. Christy, for your talk. It's very inspiring, and I'm really convinced by your data. But I hope that the fund agency will not be convinced by your data, because we need that money to do our research. Okay, and here I have some questions. And the first,
now we know how we all think.
Yeah, I totally agree with you that in the history, the Earth have experienced the climate extreme changes rate much, the changes much in larger magnitude than currently we see. However, the problem here we face, I think, is the rate. The rate of the climate change is really quick these days. According to the data in the past 30 years, I think this, just now you show that about 0.7 degrees temperature warming in the past century, but half of that magnitude take place in about past 25 to 28 years, I think. So it seems that the rate is accelerating, and that's why people are worrying about it now. And another thing that you showed examples in Greenland and California and Southeast U.S. But
Kenya too.
Yeah. But how about the other places? I mean, for example, you show the average temperature in Southeast U.S. But how about the spatial heterogeneity? And in your talk, you show that in Antarctica the ice sheet expand actually, but in Arctic the ice sheet decrease. So it seems that there was a spatial heterogeneity happened under this global change, and maybe this the differences in different places, maybe this increase. I mean, can you address about this issue? Yeah.
Okay, I think I understand the concern here is, the heterogeneity of what we see is out there. Now, I don't quite agree with you saying about the rapid changes. I can go back in history and find times when it was changing more rapidly than today on almost any variable you want to see. But that actually leads into that last point I was trying to make about how complicated the system is, and that the heterogeneity kind of tells us that the modeling systems we have today are quite crude. They cannot show Antarctica cooling and the sea ice expanding. They cannot show the heterogeneity that is really there. And so are you going to trust them to have all the processes correct for the future? And that's why we tried to get to the real bottom of the thing is, how does the climate system truly react in higher temperatures? And we did the cloud study that shows as the temperature goes up, there's this thermostatic effect that prevents, this runaway kind of warming to occur. But there's so much that needs to be known, so much more that needs to be studied. So I'm with you on continued funding. I still write proposals, so I think there's plenty of opportunity still yet to come. What I fear is the same thing that happened in other issues, is that our government will say, well, we know completely what the answer is. We're going to shut off funding to this type of science from now on.